All right, welcome everyone, or at least those of you who came to the live lecture. As a reminder, there is a new set of slides and it supersedes the old set of slides. It's on Canvas, and it contains a lot of the things that I was going to do by hand, but I now have them all typeset. I hope that there's still room for me to walk you through what's going on, but I'll give you all a chance to download those in the meantime. Are there any questions I can answer before we launch into lecture? Okay, so I am going to start from slide number 15 in the new slide set. So to set the stage or to refresh our memories, last time we went through the exercise of trying to decide what kind of threshold we should use in order to have the smallest probability of error when decoding a bit that came through a binary polar signaling scheme. So the answer was if the bits were equiprobable at the beginning, then the optimum threshold is set to be 0, and therefore we are just looking at this signal at the end of the bit period and deciding if that is positive, we'll call it a 1-bit. If it's negative, we'll call it a 0-bit. And then we have to move on with our lives because there's going to be another pulse coming through the chain. So what I want to do today is go back and answer the question, well, is there anything we can do here? Is there something, how can we filter the received noisy signal to increase our odds of deciding the correct thing down the line? And we saw, I hope, on Friday that it's not as easy as, low pass filter or high pass filter or something like that, because we don't actually know the shape of the pulse that we're sending. We're assuming a couple of things about the noise. We're assuming it's Gaussian, we're assuming it's additive, and we're assuming it's white. Those are all pretty standard assumptions. And if you make those assumptions, we can derive the power in the noise signal, which is equivalent to its variance for zero mean and ergodic, by looking at the power spectral density of the filtered noise, right? And because we're modeling it as additive noise, and because we're modeling the filter as linear, that means that we can talk about the power spectral density of this signal separate from the PSD of that signal. And so what we're doing on this line is integrating the power spectral density of the filtered noise over all frequencies to get the power, which is for ergodic processes, the same as the variance. Okay, so this is variance of sigma O. Oh, sorry, a variance. That is a circular definition, isn't it? This is the variance of NO at T, right? So if it's a Gaussian process, and at every sample, we have a Gaussian random variable. And if you pass a Gaussian process through a filter, you're going to get another Gaussian process. So this is Gaussian, zero mean, and variance sigma O squared. Okay. So, and why are we after the variance or the power or whatever you want to call it? Well, it's because of this chain of equivalences here. Is we are trying to minimize the probability that we make a mistake at the detector. And we showed that last time that's the probability that we end up in one of the tails of the bell curve. So that's, we want to minimize the area under the tail. And that's equivalent to, because Q is a monotonic function, monotonically decreasing, that's equivalent to maximizing its argument. And if I maximize a positive thing, that's the same as maximizing the square of that positive thing. All of those statements are all equivalent statements in this context. So I want to characterize the denominator of this fraction, and we've done that here. And now I want to characterize the numerator of this fraction, which is, again, we're looking at the magnitude of the filtered pulse sampled at time big T squared. We have an expression for the filtered pulse. It's simply what the filter does to the pulse. And then if I take that back into the time domain, I want an inverse Fourier transform. This is a function of t, little t, which means I can evaluate it at capital T, and the only thing that changes is the little t becomes a big T. And I think in 5 minutes, that's everything we did on Friday. Any questions? Because I do want everyone to get on the proverbial same page. Okay, so let's talk about this ratio. So this objective function, rho, I'm going to define rho as magnitude PO of t over sigma O, which implies that's rho squared is our objective function, magnitude PO of big T squared over the noise variance squared. Or sorry, the noise variance. Okay, so what I'm doing here in this line is simply plugging in the expressions we got from the last slide. So on top, that's little p sub O of big T magnitude squared. And on bottom, that is our expression for the noise variance. Okay. And then we said that we're trying to maximize this thing, maximize this argument of the Q function. So this goes back into the chain of arguments that to minimize the error, I have to maximize this function. And here, this is where I picked up on Friday. To maximize rho squared, it's not entirely clear what to do, what form h should take, because h appears both in the numerator and in the denominator. Okay. Also, h isn't just a number, right? It's a function of frequency. So we're trying to do an optimization problem where the quote-unquote independent variable isn't a number on a number line. It's not even a vector in a vector space. It's a function of an infinite domain. So this is a pretty hefty problem. So the way to go about, or one way to go about this, is to observe that we can decompose the numerator and the denominator into two functions. I'm going to call one of them x of f, and I'm going to call the other one big Y of f. And if I make these substitutions, then the numerator becomes the integral of xf times yf. Right, so the root SNFs will cancel, and I just get the integrand again. In the denominator, if I square my expression for x, if I square the magnitude of my expression for x, then I get the integrand in the denominator there. So it's a clever way of breaking up the numerator and denominator into these forms. And this is, okay, so maybe you're starting to see why I initially didn't type all this up, because this is a pretty hefty argument here. What I'd like to take a moment to observe is thinking about functions as vectors. So I'm gonna jump over here into the sidebar. One way to think about what are called square integrable functions. You and I know these as energy signals, and if I look at any signal over a finite duration of time, provided it's not infinite over that time, then we can call it a square integrable function over that period of time. You can think of those kinds of functions as a vector space, right? You can add two of them and you'll get another square integrable function. You can scale anything by a finite scalar and you will again get a square integrable function. So they fulfill all the requirements of a linear vector space. What's more is on this linear vector space, we can define the notion of inner product. And so this is, I want you to keep in mind, inner product is a generalization of your concept of dot product from, say, linear algebra, right? When you talked about dot products in linear algebra, it was always vector x dot vector y, and that would tell you something about, well, it would tell you something about their orthogonality, or it would, in the more general case, it would tell you how much of x lied in the direction of y, or something like that. We can define a similar notion, and we're going to call it an inner product, between two functions. So these are both going to be square integrable functions, which just means that the integral of their square is a finite value. And if I take their inner product, then, and I can define it this way. Take the first function, multiply by the conjugate of the second function, and integrate over all of its argument, either time or frequency, whatever. Okay, so if we define this as our inner product on that space, then we get something called the Cauchy-Schwarz inequality that has to hold true. So this is the idea. And so what Cauchy-Schwarz says is right here, this inequality. But what I want you to see is that the inner product of f with itself is, it looks like the norm of f squared. This will be the norm of g squared. So what is Cauchy-Schwarz in kind of linear algebra terms? I think you might have seen this as the inner product of vector x with vector y. You know what, I'm just going to write it with a dot product because that's, I think, what you've probably seen it as before. So the vector x dot the vector y looks like length of x times length of y times the cosine of the angle between them. Are you familiar with this notion of inner product or dot product? Have you seen that formula before somewhere? This is a manifestation of Cauchy-Schwarz in, say, Rn, right? So this says that the inner product of x with y is going to be equal to the length of x, or the norm of x, times the norm of y, times the cosine of the angle between them, but that is always less than or equal to 1. Okay, so one way to interpret this is that the inner product of two vectors is always less than or equal to the product of their norms. Okay, because cosine is always no bigger than 1. What's more, thinking about Cauchy-Schwarz in terms of this kind of cosine law for real n vectors gives us an opportunity to determine when is this inequality an equality. So actually, I'll open this up to the class. What condition has to hold so that we have equality here instead of inequality?
So the cosine theta has to equal 1.
Good.
So that means that they are parallel? Or
Yeah, collinear. Yeah, collinear is exactly what we're looking for. Right? If I have a vector and I dot it with anything, I'm going to get something less than the product of those vectors unless x and y are collinear, in which case theta is 0, and then I get equality. And this is the key to proving something about the optimal filter. So I want to pause here and make sure we all agree that this is the only way that this inequality becomes an equality, at least in Rn, in the vector space that you're comfortable with. Any questions on that?
I have a question on why is it squared? Is it just so that it's positive, I guess, if you did?
Yeah, we're going to use, and also note that there's absolute value bars here. So strictly speaking, if we're talking about the absolute value of the left, then this also works, right? Being collinear, but in the opposite direction.
Okay.
Yeah, so, and in truth, we're going to actually only be caring about absolute values. So going collinear this way or anti-collinear that way, it works the same for us.
Okay, thank you.
Cool. So what I want you to see is that this expression looks like well, that looks like this expression, doesn't it? Maybe a little bit. Maybe I can clean some of this up here. So let's forget about the absolute value bars for now, and let's focus on the integral. So this integral is an integral over all frequencies, and it's an integral of one function times another function. So I think this is inner product of capital X of f, not quite with y, right? And this is the one super minor nuance here. Well, this is the minorest of nuances here. And this is actually the inner product of x with y conjugate. Because when we end up taking the integral, we have no conjugate, and this tells me I need a conjugate, so I need to pre-conjugate. So I end up with no conjugate. Okay, so the numerator, at least within the absolute value bars, is the inner product of x with y star. And I hope you can now see that the numerator and this are going to be one and the same. Yeah. So this is why, I'm going to use Cauchy-Schwarz on the numerator here. The other thing to recognize is, well, no, I think that's good. So I think we can go to the next slide unless there are any questions here. Okay, so here is this. Cauchy-Schwarz gives us this inequality because the numerator on the left has to be no bigger than the numerator on the right. And this is inner product of x with x. And this is, oh, sorry, there's a df here. This is inner product of y star with y star. And then here's the key. Here's the notion that this inequality only becomes an equality if the two functions are quote unquote collinear. Another way to say that is one function is a scalar multiple of the other function. So for any scalar, in our case, it's going to be a real scalar. Right, so this is us using that kind of cosine law of dot products to say, hey, this bound is strict unless x and y star are pointing, quote unquote, in the same direction. Okay, thinking about functions as vectors, if x and y star are pointing in the same direction, the mathy way of saying that is x is a scalar multiple of y star, and vice versa. Okay, and so from here, we're home free. From here, well, I guess from here, we're just using stuff that we've already defined. The key argument has already been made, is that the function we're trying to optimize is always smaller than this thing, except it equals this thing when this is true. And we want to make this true. That way, the objective function is as big as possible. That's the big picture here. Okay, so what does it mean for x and y star to be collinear? Well, I'm just subbing in, so sub in y of f here from the definition on, what, 2 slides ago. And so I have to conjugate it, so the p becomes p star, the e to the positive j whatever becomes e to the negative j whatever, and the root of the power spectrum density of the noise becomes the conjugate of that. No big deal. This is because conjugation passes into fractions and out of fractions. No problem. Okay, so now we have a shape, or we have a functional form for x to give us the maximum SNR. If we do that, so this notation, this is the filter, or I'll say the optimal filter, or the filter when x has this property. So any old filter is h of f, the optimal filter, I'm going to give it a hat. It's special. It gets a hat. Okay, and then what we're doing here is this is x of f. This is our definition of x. And so if I sub in the optimal x, I get the optimal filter in there. And if the only trickery here on the right-hand side is that I move the conjugate inside of the square root, and that's because square rooting doesn't change the, you can conjugate before or after the square root. Okay, last but not least is I just solve for the optimal filter here. I divide through by root Sn of f, and I get Sn of f star times Sn, which is the magnitude of Sn of f. Take the square root of that. I lose the power 2. What else am I doing here? So you'll see that the p star of f became p of negative f. And it's called Hermitian symmetry or conjugate symmetry. And this is true if p is a real function. If p is real, then its Fourier transform has conjugate symmetry. If I go negative f hertz, I'll get the conjugate as if I went positive f hertz. Okay, there's a lot that went on in this slide, and normally I would take the time to write it all out, but I'm kind of blowing through it because I've already written it out. So I want to pause here for questions or digestions.
Quick clarification. Why are we maxing rho squared again?
Yeah, let's go back to this chain of arguments here. So we'll work backwards this time. This is rho squared, which is equivalent to maximizing rho, which is equivalent to minimizing q of rho, which is essentially equivalent to minimizing the probability of error.
Okay.
This is q of rho in our new notation.
Okay, thank you.
Yep. Okay. Yeah, so this is where we left off. And
for the filter, does the k matter, like which k you pick?
It doesn't. They'll all be optimal as long as you pick k. Picking k equals 1 doesn't hurt you because this is true for any scalar k. It also means that you don't need a whole lot of gain in the filter, because that's really what k would represent here. It would be a broad frequency gain. It means that if you're, say, power limited, then you can set the broad spectrum gain to be whatever you can do, and you'll get the optimal result.
Cool.
And yeah, the key observation there is that by scaling the pulse in the frequency domain, you're also scaling the noise in the frequency domain. If you scale them by the same amount, then you're not helping or hurting yourself. Okay, so I think on the next slide, we're going to make an assumption about the power spectral density of the noise. And if the noise we assume is white, remember the power spectral density of white noise is flat. PSD of white noise. And so for reasons that I have still not figured out, this level is, at least in the Lothy book, defined as script n over 2. And I get the over 2, but the script n is still baffling to me why he chose that symbol. But I'm just going to go with it. Okay. So then what have we done here? We have subbed in, remember, h hat of f on the previous slide was p of minus f, capital P, minus f, e to the minus j, 2 pi ft over magnitude Sn. Okay, so we get, instead of divide by n over 2, we get multiply by 2 over n, and then that gets us to this line. And the last step is going into the time domain. So from here to here, I'm taking an inverse Fourier transform. So we have a frequency reversal becomes a time reversal by duality, and a complex phase becomes, a complex phase addition becomes a time delay or advance in whatever sign you have here. Okay. So those are two basic Fourier transform properties. That reversal of frequency will also reverse your time, and then this is the Fourier transform of a time delay, which becomes a time advance in reverse time. Couldn't be easier, right? But before we go to the next slide, does this look familiar to anyone?
It looks like what we did at the beginning with like radar stuff.
It looks like the radar problem in which we had to use a causal match filter. This is one of my favorite parts of this course, is that we do all of this work and we get back to a match filter. And I think that probably says more about my personality than I would normally care to share. But the fact that we did all that work and we get back to something that we kind of intuitively knew was the best way to pick a signal out of noise. Right. So yeah, this is why I assigned that question in the first homework, is because you see it again here. Does anyone need help seeing it? All right. So now that we know what the optimal filter should be, so given h hat of f, we can actually go back and compute x hat of f. And it turns out that our expression for rho, this is now, rho also has a hat, so this is now the optimal, or the SNR under optimal filtering. How about that? I've hesitated to call this the SNR, but that's actually what it represents, because I think a lot of people think of SNR as being measured at the receive antenna. But this is not that, right? This is the SNR of filtered signals. And so what we're trying to do is we're trying to, and often you can't do anything about the SNR at your receive antenna, but what we're trying to do is we're trying to massage the spectra such that after filtering, we've maximized SNR. So one way to think about that is we're tamping down the noise where we can, and we're boosting the signal where we can. That's another equivalent way of thinking of this. So the objective function, or the SNR, under optimal filtering, you get to cancel those two terms. And remember, this Cauchy-Schwarz says this is less than or equal to, but what we're doing is we're only taking the equals, right? Because we're assuming optimality, or we're enforcing optimality. Okay, so now we get to plug in our expression for y. So plug in your expression for y. Also noting that the magnitude of y star is the same as the magnitude of y. So magnitude y star, magnitude of y. That's how I drop the star from here to there. And so what do we get? And then we assumed, so this is our white noise assumption. In case you hadn't realized, this whole exercise becomes way harder if you don't assume white noise. If you have a situation where the noise is colored or is spiking at one frequency, you can still use this analysis up until where I assumed white noise. You don't get a nice clean answer. And so this is my justification for why this is the signal to noise ratio, right? This is the energy in our pulse and this is the noise power. Okay, so this is literally signal over noise. Let's see, what do we got on the next slide? So I think I'm going to abbreviate this as energy in the pulse, E sub p. And so if you go back to our probability of error, it was, what was Q of rho, wasn't it? And so if you allow me, I'm going to substitute P sub E for P of error. The optimal, or the best, error probability is then going to be Q of rho hat. And so we have just shown that that's Q of square root of twice the energy in the pulse divided by the noise power. Or energy in the pulse divided by the power spectral level of the noise, right? Because we define that to be script n over 2. There's something to be said about this expression, and that is, what should the pulse be? Right? We've been kind of looking at this problem from the finish and then working our way back to the start. We first established what the threshold ought to be, and now we've established what the filter ought to be to maximize SNR after the filter. But if you go one step earlier in the kind of chain of this communication system, you get to, well, what the heck was the pulse in the first place? We've assumed it's an energy signal. That's not a huge problem because you want it to be finite duration. You want it to be finite, so that's the definition of an energy signal. Does this expression, does this probability of error tell us what the shape of the pulse should be? Nope. But what's more, not only that it doesn't tell us, but it tells us something else. It tells us that the probability of making a mistake is independent of the shape of the pulse, provided the two pulses you're considering have equal energy. And that is a pretty cool result. It is a consequence of a bunch of the assumptions that we made, including linear filtering and white noise. But this is a massively important result. And it could slip right by us if we don't note it, right? The probability of making a mistake is a function of the noise power and the pulse energy only, not the shape of the pulse at all. All right. And lastly, so this is the picture that we've got so far. This commutator closes at t equals big T. And then we take the result of that and we put it through the threshold detector. And this is then either 1 or 0, depending on the SIGN of this signal. And right, this was our received antenna. So I want you to see that we can get the effects of match filtering without having anything that actually would look like a matched filter. So my claim is that this is equivalent to having R of t come in to a multiplier, which we're feeding some kind of locally generated pulse copy. And then the key here is integrate. So my claim, and I'll show you why this is true, my claim is that the dashed box here is equivalent to the dashed box here. And what I mean by that is that you and I can't tell in a black box situation which of these two, if we only get to look here and here, we only get to look there and there, we can't tell which of these two is being used. And I can tell you that this one is more practical. Okay, so let's see why that is true. So let's go back to blue. So this signal is P of little t convolved with P of t minus t, plus some noise, but I'm just going to focus on the first term here. Okay. And if we just go back to our roots of convolution, integrating over all time of the first at a dummy times the second time reversed dummy, so big T minus t minus the dummy. Well, I mean, I'm just going to distribute in here. P, and of course, these don't have to be infinite integrals if P is time limited, right? So if P of tau is only limited to a finite range of taus, then just integrate from 0 to that range of taus. P of tau times P of, what do we get here? Big T minus little t plus tau. And so what should we call this signal? Let's call it y. I'm going to call that y of t. And if I evaluate y of little t equals to big T, so that's what we're doing here. I plug in everywhere I see a little t, I plug in a big T, and I get the integral of P of tau times P of tau, d tau. And that's exactly what we get here. P of t plus the noise. If I multiply P of t with P of t, integrate the result, and then dump or sample that at t equals big T, this is equal to what you would get if you sampled this at big T as well. So the idea is that you can mathematically show that the matched filter is ideal, but then in practice, you don't actually have to build a system whose impulse response just happens to be the time reverse value of your pulse, which in practice is kind of a difficult operation to achieve. What's an easier operation to achieve is to program some generator to generate the pulse and reset every bit. And then this is called an integrate and dump operation. Integrate and dump. The idea being that this isn't like a true integral that winds up over all time. You integrate over one bit period, then you dump the result. Then you start integrating again, then you dump the result. And dump this in this situation means pass the result of your integral down to the threshold detector. So this will help us in the future when implementing matched filtering is costly or difficult. We'll often do this same operation where we multiply by the known pulse and then integrate the result. And this is to show that those are equivalent operations. How are we doing? Any questions? Because I think the next slide switches to a new topic.
So the two P's that are exiting from the main big block, like the P, T, star P, big T minus, is that independent of the P going into the multiplier where there's an R?
So this pulse has to be matched to this pulse. So there's still matching going on. You just don't have to build a circuit whose impulse response happens to be a time reversed version of your pulse. You can run the pulse in positive time or in forward time and just integrate the result. The assumption being that if you can generate the pulse at the transmitter, you can also generate the pulse at the receiver. And integrating is a easier operation than building a circuit that magically has this time reversed impulse response. All right. So like, as I said, this is kind of a shift in topic, but it will open the door to results down the road.
Wait, I have a question, quick
Go ahead.
question. In the beginning, when we talked about radar, we assumed the match filter was just a time reversed version of the signal. Why did this one just happen to be causal? Like the other one, we had to make it causal by like shifting it. Why didn't we have to do that for this one?
So when we came up with the radar ranging, I basically just said, let's do an autocorrelation or a cross correlation. And so strictly speaking, doing quote unquote doing a cross correlation doesn't have a time shift. But if you cross correlate, if you want your system to be causal, right? So if I impose a cross correlation, that doesn't necessarily imply causality. So we got a result, and then we had to make it causal. Here, there is an assumption, implicit assumption of causality, because we started with this is a filter, this is a buildable filter, h of f, and we need to get a causal result out the other side. I think a lot of books will quite often, a lot of books will gloss over this fact because they're not comfortable with presenting complex analysis or something like that. And so, but if you actually look at what I walk through, having this conjugate here was a big part of flipping time around and then shifting by capital T. So I guess not all books are created equal, and being comfortable with your inner product having a complex conjugate in there actually makes the result that much nicer for engineers anyway.
Thanks.
Okay, so this is good that we're doing this at the end of this lecture because it's in the same theme, because it's talking about signal spaces. And I try to stress this when I talk about Fourier series in 228 because of this lecture in 416, basically. So you all, this is the payoff. So what I want to start thinking about is think about a vector space, and that vector space ought to be spanned by basis vectors. And I'm just going to call those basis vectors phi sub n. They happen to be functions because we're talking about function spaces where vectors are functions. But at the very get-go, if you're comfortable with vector spaces being spanned by a basis, that's all this is. Technically speaking, when we're talking about infinite dimensional vector spaces, there are an infinite number of these. But the fact that there's an infinity of these isn't that important right now. Examples of this for kind of square integrable spaces are e to the j n omega naught t, or things like cosine n omega naught t paired with sine n omega naught t. So these are the kinds of things that that you've seen that fit this bill. So if I have a set of basis vectors, then really the best thing to do with those basis vectors is to use them to construct vectors in the space, right? That's why basis vectors are nice. You can get to anywhere in the space by taking a linear combination of those basis vectors. So how much of each basis vector we get from this amount? So again, if we take the R2 example, if I want to get to this point in R2, I can go this far along basis vector U1, and I can go this far along basis vector U2, and I can get to anywhere I want in the space, provided I know S1 and S2, right? The lengths of these vectors are the scaling factors. It's the same exact story here. We're scaling basis functions by how much? Well, that's why we use projection. So S sub n is going to be the projection of the function that we'd like onto the basis function that we want to go along, divide by the, well, this is the norm of the basis function squared. Right, so this is, you saw the same formula in your linear algebra class, but it was more along the lines of inner product of x with basis vector u1 divided by magnitude of u1 squared. And if u1 has unit magnitude, boom, you lose the denominator. So that's why orthonormal basis functions are nice, because you get to forget about the denominator here because they all have magnitude 1. Okay, so the part of this lecture that I'm just going to ask you to take on faith, because I don't think we're equipped to actually prove this at this point, is the following claim. And that is, if x of t is a white noise process, then the following holds. Then there exist these x sub n's, capital X sub n's, such that if I look at the area under the square of the difference between, this is kind of our best in space approximation. Right? This is the closest we can get if you think of, I don't know if this is going to help or hurt, but we'll give it a shot. If I'm restricted to the space and I say I want to get to that vector, then the best I can do is get to maybe here. And then this is the error that we have. And what I'm saying in this claim is that this error has magnitude 0. Okay. Or we say, sometimes you'll see this as the white noise process x of t equals, in the mean square sense, this linear combination of basis vectors. Okay, but that's an equal sign underneath the letters ms for mean square. Now, that all sounds well and good until you actually start to think about it for half a second, because if this is a noise process, that means it's random, right? And what part of this is random? Not the basis functions, right? The basis functions are things like deterministic sines and cosines, deterministic complex exponentials. And so, I mean, by process of elimination, these have to be random. Okay, so we can write a white noise process as a Fourier series, quote unquote, provided the coefficients of that Fourier series are random variables. Right, I can't escape the fact that x of t is a random process, and so there has to be some randomness in the way that we generate it out of these basis functions. The basis functions themselves aren't random, so therefore the coefficients must be. That's my kind of roundabout argument for why this has to hold. Let's see what's next. Ah, there we go. To compute these coefficients, we are going to project. Right, so this is the inner product of x with phi sub n, assuming all of the phis are unit magnitude or unit norm. Okay. So here we're taking an integral of a random function times a deterministic function. So this is another argument as to why these are going to have to be random variables. Okay, and the big payoff out of all this argument is that if x of t, in addition to being white, is a Gaussian random process, then the really cool thing, and the thing that doesn't have to be true for a general distribution, is that the coefficients x sub n will themselves be jointly Gaussian. And we'll cover why that's important and why it makes our lives simpler next time. Thanks, everyone.